Hello everyone. Welcome to Rush Learning Hub. I hope you are doing well and preparing confidently for the UGC NET Environmental Sciences examination. Today, we are beginning Unit 7, Solid and Hazardous Waste Management, one of the most important units in the UGC NET Environmental Sciences syllabus. Every year, questions from this unit appear in the examination, so understanding each concept clearly is extremely important. Before we begin, let me ask you a simple question. Have you ever wondered what happens to the waste we throw away every day? Every morning, millions of people throw away food waste, plastic bottles, paper, broken electronic items, batteries, and many other unwanted materials. We simply put them in a dustbin and forget about them. But does the waste actually disappear? The answer is no. Once waste leaves our homes, it enters a complete management system that includes segregation, collection, transportation, processing, recycling, treatment, energy recovery, and final disposal. If this system is not managed properly, waste begins to accumulate in streets, rivers, lakes, forests, and oceans. It pollutes the environment, spreads diseases, contaminates groundwater, and contributes to climate change. That is why solid waste management has become one of the greatest environmental challenges of the 21st century. Now let us understand the meaning of solid waste. Solid waste is any unwanted or discarded solid or semi-solid material generated by human activities. It is produced from households, schools, colleges, offices, industries, hospitals, markets, agricultural fields, and construction sites. Examples include food waste, paper, plastics, glass, metals, textiles, garden waste, construction debris, and many other materials. One important concept to remember is that waste is not always useless. What is waste for one person may become a valuable resource for another. Paper can be recycled into new paper products. Plastic bottles can be converted into new plastic materials. Kitchen waste can be transformed into compost or biogas. Therefore, modern environmental science considers waste as a resource rather than simply garbage. Now let us understand hazardous waste. Hazardous waste is any waste that possesses properties capable of causing harm to human health or the environment. These properties include toxicity, corrosiveness, ignitability, and reactivity. Examples include industrial chemicals, pesticides, heavy metals, biomedical waste, used batteries, waste oils, solvents, paints, and electronic waste. Unlike ordinary municipal waste, hazardous waste requires special handling, transportation, treatment, and disposal because improper management can seriously pollute the environment and threaten public health. For example, heavy metals such as lead and mercury can contaminate groundwater and enter the food chain. Biomedical waste can spread infectious diseases if it is not treated properly. This is why hazardous waste management is one of the most important areas of environmental protection. Now let us understand why waste management is necessary. Imagine a city where waste is never collected. Within a few days, garbage would accumulate on roads. Bad odors would spread throughout the city. Flies, mosquitoes, and rodents would multiply rapidly. Rivers and lakes would become polluted. As organic waste decomposes, methane gas would be released into the atmosphere, contributing to global warming. Rainwater passing through waste would produce leachate, which could contaminate groundwater. Such conditions would create serious environmental and public health problems. Therefore, proper waste management is essential to protect human health, conserve natural resources, reduce pollution, recover valuable resources, and achieve sustainable development. Now let us discuss one of the most important concepts for the UGC NET examination, the waste management hierarchy. The first and most preferred option is reduce. The best waste is the waste that is never produced. Reducing unnecessary consumption directly decreases waste generation. The second option is reuse. Many products can be used repeatedly instead of being thrown away after a single use. The third option is recycle. Materials such as paper, plastic, glass, and metals can be processed into new products, reducing the demand for fresh natural resources. The fourth option is recover. If recycling is not possible, waste can still be converted into useful forms of energy through technologies such as biomethanation and waste-to-energy plants. The final option is dispose. Disposal through sanitary landfills or incineration should always be the last option after reduction, reuse, recycling, and recovery have been considered. For the examination, remember this sequence. Reduce, reuse, recycle, recover, dispose. Now let us look at the main objectives of solid waste management. The first objective is to protect public health. The second objective is to conserve natural resources. The third objective is to prevent environmental pollution. The fourth objective is to recover useful materials and generate energy from waste. The fifth objective is to promote sustainable development by minimizing environmental impacts. Before we move to the next slide, remember one important point. Solid waste management is not simply the collection of garbage. It is a scientific process that includes waste generation, segregation, storage, collection, transportation, processing, recycling, treatment, energy recovery, and final disposal. Every stage is equally important for protecting the environment and ensuring a cleaner and healthier future. Now, let us move to one of the most important topics for the UGC NET examination, solid waste, types, sources, and characteristics. To manage waste effectively, we must first understand what kind of waste is being generated. Different types of waste require different methods of collection, treatment, recycling, and disposal. Therefore, classification of solid waste is the foundation of scientific waste management. Let us first discuss the types of solid waste. The first type is municipal solid waste, commonly known as MSW. This includes waste generated from households, shops, offices, schools, hotels, markets, parks, and streets. Examples include food waste, paper, plastics, glass, textiles, garden waste, and street sweepings. Municipal solid waste forms the largest component of urban waste. The second type is industrial solid waste. This waste is generated during industrial manufacturing and processing activities. Examples include fly ash from thermal power plants, slag from steel industries, chemical sludge, scrap metals, packaging materials, and manufacturing residues. Some industrial wastes are non-hazardous, while others are hazardous because they contain toxic chemicals. The third type is agricultural waste. Agricultural waste is produced from farming activities and includes crop residues, straw, husk, bagasse, animal manure, fruit and vegetable waste, and pesticide containers. Many agricultural wastes can be converted into compost, biogas, or biofuels, making them valuable renewable resources. The fourth type is construction and demolition waste. This waste is generated during construction, renovation, and demolition of buildings. It includes concrete, bricks, wood, steel, glass, plaster, and tiles. Recycling construction waste helps conserve natural resources and reduces the burden on landfills. The fifth type is biomedical waste, generated from hospitals, clinics, laboratories, blood banks, and veterinary facilities. Examples include used syringes, contaminated dressings, pathological waste, and expired medicines. Biomedical waste requires special treatment because it may spread infectious diseases. The sixth type is electronic waste or e-waste. This includes discarded electrical and electronic equipment such as computers, mobile phones, televisions, printers, refrigerators, batteries, and circuit boards. E-waste contains valuable metals like gold and copper, but also hazardous substances such as lead, mercury, and cadmium. Now let us discuss the sources of solid waste. Solid waste originates from several sources, including residential areas, commercial establishments, institutions, industries, agriculture, construction activities, municipal services, treatment plants, and mining operations. Remember this simple order for the examination: residential, commercial, institutional, industrial, agricultural, construction, municipal services, treatment plants, and mining. This sequence is useful for multiple choice and matching questions. Now let us understand the characteristics of solid waste. The characteristics of waste help environmental engineers decide the most suitable treatment and disposal methods. The first category is physical characteristics. These include moisture content, density, particle size, porosity, field capacity, and compressibility. Moisture content is particularly important because waste with high moisture is suitable for composting and biomethanation but less suitable for incineration. Density affects transportation and landfill design, while particle size influences recycling and biological treatment processes. The second category is chemical characteristics. These include pH, calorific value, organic matter content, carbon, nitrogen, phosphorus, potassium, ash content, and volatile matter. Calorific value is especially important because it indicates the energy-producing potential of waste. Waste with a high calorific value can be used in waste-to-energy plants or for producing refuse-derived fuel, commonly known as RDF. The third category is biological characteristics. These determine whether waste is biodegradable or non-biodegradable. Biodegradable waste includes food waste, leaves, paper, wood, and agricultural residues. These materials can be decomposed naturally by microorganisms and converted into compost or biogas. Non-biodegradable waste includes plastics, metals, glass, and synthetic materials. These materials persist in the environment for long periods and require recycling or scientific disposal. Now let us understand another important concept, the generation rate of solid waste. Generation rate refers to the amount of waste produced by an individual per day. It is usually expressed in kilograms per capita per day. Waste generation depends on population size, economic development, lifestyle, urbanization, and consumption patterns. Developed countries generally produce more waste per person than developing countries. In India, municipal solid waste contains a higher proportion of biodegradable organic matter compared to many developed nations. Now let us study two very important analyses frequently asked in the UGC NET examination: proximate analysis and ultimate analysis. Proximate analysis determines four important components of waste: moisture content, volatile matter, ash content, and fixed carbon. This analysis helps evaluate combustion characteristics and energy recovery potential. On the other hand, ultimate analysis determines the elemental composition of waste. It measures carbon, hydrogen, oxygen, nitrogen, sulfur, and sometimes chlorine and ash. Ultimate analysis is useful for estimating calorific value, combustion efficiency, and pollution potential. Students often confuse these two analyses. Remember this simple trick. Proximate analysis studies fuel fractions, moisture, volatile matter, ash, and fixed carbon. Ultimate analysis studies chemical elements, carbon, hydrogen, oxygen, nitrogen, and sulfur. This difference is frequently asked in UGC NET examinations. Before we move to the next slide, let us quickly revise. Solid waste can be classified into municipal, industrial, agricultural, construction, biomedical, and electronic waste. Its physical, chemical, and biological characteristics determine the most suitable collection, treatment, recycling, and disposal methods. Generation rate helps estimate waste quantity, while proximate and ultimate analyses help evaluate waste properties for energy recovery and environmental management. Let us move to the next important topic in the UGC NET Environmental Sciences syllabus, solid waste collection and transportation. Collection and transportation form the backbone of any solid waste management system. Even if a city has excellent recycling plants, composting facilities, and sanitary landfills, the entire system will fail if waste is not collected and transported efficiently. Therefore, an effective collection and transportation system is essential for maintaining public health and environmental cleanliness. The first step is waste storage at the source. Before waste is collected, it should be stored properly in suitable containers. Modern waste management encourages source segregation, where biodegradable waste, recyclable waste, and hazardous household waste are kept in separate containers. Segregation at the source improves recycling efficiency, reduces treatment costs, and minimizes environmental pollution. Now let us discuss container systems, which are an important topic for the UGC NET examination. There are two major types of container systems. The first is the hauled container system. In a hauled container system, the entire waste container is transported to the disposal or processing site. After the waste is unloaded, the empty container is brought back to its original location or replaced with another empty container. This system is generally used where large quantities of waste are generated, such as industries, construction sites, markets, and commercial complexes. The main advantages of the hauled container system are efficient handling of large waste volumes, fewer collection trips, and reduced manual handling. However, the disadvantages include higher transportation costs and the requirement for specialized vehicles. The second type is the stationary container system. In this system, the waste container remains at the collection site. Collection vehicles visit the location, empty the waste into the vehicle, and return the container to its original position. This system is commonly used for residential areas, schools, offices, and commercial establishments. Its advantages include lower equipment costs, convenient operation, and suitability for regular municipal waste collection. For the UGC NET examination, remember this simple difference. Hauled container system, the container moves with the waste. Stationary container system, the container remains at the collection site while only the waste is transported. This comparison is frequently asked in objective examinations. Now let us understand collection routes. A collection route is the planned path followed by waste collection vehicles to collect waste from different locations in the shortest possible time. Proper route planning reduces fuel consumption, labor costs, vehicle wear and tear, and collection time. Environmental engineers use route optimization techniques to maximize efficiency while minimizing operational costs. Factors affecting route planning include population density, road conditions, traffic congestion, waste generation rate, collection frequency, vehicle capacity, and distance to the disposal site. Efficient route planning is an important component of modern smart city waste management systems. Next, let us discuss transfer stations. A transfer station is an intermediate facility where waste collected by small collection vehicles is temporarily unloaded and transferred into larger transport vehicles. Instead of every small collection vehicle traveling long distances to a landfill or treatment plant, waste is first brought to a transfer station. At the transfer station, the waste is compacted and loaded into large trucks or trailers for transportation to the final processing or disposal site. Transfer stations reduce transportation costs, save fuel, decrease traffic congestion, improve collection efficiency, and increase vehicle productivity. They are particularly useful in large metropolitan cities where disposal facilities are located far from urban centers. Now let us understand the transportation of solid waste. After collection, waste must be transported safely to recycling plants, composting facilities, waste-to-energy plants, sanitary landfills, or other treatment facilities. Transportation vehicles should be properly covered to prevent waste from falling onto roads and to minimize odor, dust, and littering. Regular maintenance of vehicles is also essential to prevent leakage of leachate and ensure efficient operation. Today, many cities use GPS-based vehicle tracking systems to monitor waste collection vehicles in real time. This improves operational efficiency, reduces unnecessary delays, and helps municipal authorities monitor collection performance. Modern waste management also uses compactor vehicles, which compress waste during transportation. Compaction increases the amount of waste carried in a single trip, thereby reducing transportation costs and fuel consumption. Now let us quickly revise the key concepts. There are two types of container systems. In the hauled container system, the entire container is transported. In the stationary container system, the container remains at the collection point while only the waste is transported. A collection route is the planned path followed by collection vehicles. A transfer station is an intermediate facility where waste is transferred from smaller vehicles to larger transport vehicles. Proper transportation ensures safe, economical, and environmentally sound movement of waste to treatment or disposal facilities. For the UGC NET examination, remember these important points. Hauled container system, container moves. Stationary container system, container stays. Transfer station, intermediate waste transfer facility. Route optimization reduces fuel, time, and operational cost. These concepts are frequently asked in conceptual and statement-based questions. Now that we have understood how waste is collected and transported, the next question is, what happens after waste reaches the treatment facility? What happens after the waste reaches the processing plant? Does every kilogram of waste go directly to a landfill? The answer is no. Modern waste management considers waste as a valuable resource rather than simply garbage. Many materials present in municipal solid waste can be recovered, recycled, or converted into useful products. This approach reduces environmental pollution, conserves natural resources, and supports sustainable development. This concept is known as resource recovery. Resource recovery means extracting useful materials or energy from waste before its final disposal. It is one of the most important principles of modern solid waste management and plays a major role in the circular economy. The first step in resource recovery is segregation. Segregation means separating waste into different categories according to its physical and chemical characteristics. Segregation can be carried out in two ways. The first is source segregation, where households separate biodegradable waste, recyclable waste, and hazardous waste before collection. The second is centralized segregation, which takes place at treatment facilities after waste has been collected. Source segregation is always preferred because it improves recycling efficiency, reduces contamination, lowers treatment costs, and increases the quality of recovered materials. Now let us discuss material recovery facilities, commonly called MRFs. A material recovery facility is a specialized plant where mixed municipal solid waste is sorted and valuable recyclable materials are recovered before final disposal. Different technologies are used in material recovery facilities. Magnetic separators remove iron and steel. Air classifiers separate light materials from heavier materials. Screens separate waste based on particle size. Optical sorting systems identify different types of plastics. In many developing countries, manual sorting is also carried out to recover recyclable materials. Recovered materials such as paper, cardboard, plastics, glass, aluminum, and steel are then supplied to recycling industries for manufacturing new products. Now let us understand recycling. Recycling is the process of collecting, processing, and converting waste materials into new useful products. Recycling reduces the need for fresh raw materials and helps conserve natural resources. For example, waste paper is converted into new paper products. Plastic bottles are processed into plastic granules used to manufacture new plastic products. Scrap metals are melted and reused in various industries. Glass bottles are crushed, melted, and manufactured into new glass products. Recycling provides many environmental benefits. It reduces landfill requirements. It conserves natural resources. It saves energy. It reduces greenhouse gas emissions. It decreases environmental pollution. It also creates employment opportunities in recycling industries. However, successful recycling depends on proper segregation. If recyclable materials become contaminated with food waste or hazardous substances, recycling becomes difficult or even impossible. Therefore, source segregation is the foundation of an effective recycling. Direct manufacture of solid waste products. Instead of recovering raw materials, some waste materials can be directly converted into useful products. Examples include plastic lumber made from waste plastics, paving blocks produced from industrial waste, fly ash bricks, compost prepared from biodegradable waste, and recycled construction materials used for road construction. These technologies reduce waste generation while creating valuable products from discarded materials. This approach supports the concept of a circular economy. In a circular economy, products and materials remain in use for as long as possible through reuse, repair, recycling, and recovery, instead of following the traditional pattern of use and disposal. Now let us understand why resource recovery is so important. Recovering useful materials reduces pressure on natural resources. It decreases mining and deforestation. It saves energy. It reduces pollution. It minimizes greenhouse gas emissions. It also extends the lifespan of sanitary landfills by reducing the amount of waste requiring final disposal. From the UGC NET examination point of view, remember these important facts. Resource recovery means recovering useful materials or energy before final disposal. Material Recovery Facility, or MRF, is a facility where recyclable materials are separated from mixed municipal solid waste. Source segregation is more efficient than centralized segregation. Recycling conserves natural resources, saves energy, reduces pollution, and supports sustainable development. Before moving to the next slide, let us quickly revise. Waste should first be segregated. Valuable materials are recovered in material recovery facilities. Recovered materials are recycled into new products. Some wastes are directly converted into useful products. These processes reduce landfill burden and support a circular economy. We learned that many valuable materials can be recovered from waste before final disposal. But an important question still remains. What happens to the waste that cannot be recycled? Can it still be useful? The answer is yes. Modern environmental engineering has developed several technologies that convert non-recyclable and biodegradable waste into useful forms of energy. These technologies reduce the amount of waste reaching landfills while generating renewable energy. This approach is known as waste-to-energy or WT. Waste-to-energy refers to the process of converting solid waste into useful energy such as electricity, heat, or fuel. Instead of treating waste as a burden, this approach treats it as a valuable energy resource and supports sustainable development. One of the simplest methods of energy recovery is the production of fuel pellets. Fuel pellets are manufactured by drying, shredding, compressing, and densifying combustible solid waste. Materials commonly used include paper, cardboard, sawdust, agricultural residues, plastic fractions, and textile waste. Because of their low moisture content and high density, fuel pellets have a high calorific value. They are widely used as an alternative fuel in cement industries, industrial boilers, and furnaces. Compared with loose waste, fuel pellets are easier to store, transport, and burn efficiently. Another important technology is refuse-derived fuel, commonly known as RDF. Refuse-derived fuel is produced after removing recyclable materials and non-combustible substances from municipal solid waste. The remaining combustible fraction, mainly consisting of paper, plastics, textiles, rubber, and wood, is shredded and processed into RDF. RDF is commonly used in cement plants, industrial boilers, and thermal power stations as a substitute for coal. For the UGC NET examination, remember one important difference. Fuel pellets are manufactured compressed fuels, whereas RDF is the processed combustible fraction of municipal solid waste. Both are used for energy generation, but they are not exactly the same. Now let us move to biological treatment methods, which are suitable for biodegradable waste. The first biological treatment method is composting. Composting is the controlled aerobic decomposition of biodegradable organic waste by microorganisms. The word aerobic means decomposition takes place in the presence of oxygen. Organic wastes such as vegetable peels, fruit waste, food waste, leaves, crop residues, and garden waste are converted into compost. Compost is a nutrient-rich organic manure that improves soil fertility, enhances water holding capacity, and increases microbial activity in soil. Composting also reduces the amount of waste sent to landfills and lowers greenhouse gas emissions. Several factors influence composting efficiency, including temperature, moisture, oxygen supply, particle size, and the carbon-to-nitrogen ratio. For the UGC NET examination, remember that the ideal carbon-to-nitrogen ratio is approximately 30:1. Now let us discuss vermicomposting. The word vermi means worms. Vermicomposting uses earthworms, especially species such as Icenia fetida, along with microorganisms to convert organic waste into nutrient-rich vermicompost. Compared with ordinary compost, vermicompost contains higher amounts of plant nutrients, beneficial microorganisms, enzymes, and plant growth-promoting substances. It improves soil structure, increases water retention, enhances aeration, and promotes sustainable agriculture. Students often confuse composting and vermicomposting. Remember this simple difference. Composting uses microorganisms only. Vermicomposting uses earthworms along with microorganisms. Now let us study another important biological treatment method, biomethanation. Biomethanation is the anaerobic decomposition of biodegradable organic waste. The word anaerobic means decomposition occurs in the absence of oxygen. During this process, anaerobic microorganisms break down organic matter and produce biogas. Biogas mainly contains methane, carbon dioxide, and small amounts of hydrogen sulfide and water vapor. Methane is the combustible component responsible for energy production. The generated biogas can be used for cooking, heating, electricity generation, and even as vehicle fuel after purification. The remaining material after biomethanation is called digestate. Digestate is rich in nutrients and can be used as an organic fertilizer. Biomethanation is particularly suitable for kitchen waste, food processing waste, animal dung, market waste, and agricultural residues. Compared with landfilling, biomethanation helps reduce greenhouse gas emissions because methane is captured and utilized instead of escaping into the atmosphere. Now let us compare the three biological treatment methods. Composting is an aerobic process that produces compost. Vermicomposting uses earthworms and microorganisms to produce vermicompost. Biomethanation is an anaerobic process that produces biogas and digestate. This comparison is frequently asked in UGC NET examinations. Before we move to the next slide, let us quickly revise the important points. Fuel pellets and RDF are used for energy recovery from combustible waste. Composting converts biodegradable waste into compost through aerobic decomposition. Vermicomposting uses earthworms to produce nutrient-rich vermicompost. Biomethanation converts biodegradable waste into methane-rich biogas under anaerobic conditions. These technologies reduce landfill burden, conserve resources, generate renewable energy, and support sustainable waste management. In the previous slide, we learned about energy recovery, composting, vermicomposting, and biomethanation. These methods significantly reduce the quantity of waste requiring disposal. However, even after recycling and treatment, some waste still remains. So, the next question is, what should we do with this remaining waste? The answer is scientific disposal. Disposal is the final stage of solid waste management. It involves the safe and environmentally sound placement of residual waste so that it does not pollute the environment or pose risks to human health. The two most important disposal methods included in the UGC NET Environmental Sciences syllabus are sanitary landfilling and incineration. Let us first understand sanitary landfilling. A sanitary landfill is an engineered waste disposal facility where solid waste is disposed of using scientific methods to minimize environmental pollution. Unlike open dumping, a sanitary landfill is carefully designed with protective engineering systems that prevent contamination of soil, groundwater, and surface water. Open dumping is one of the most harmful methods of waste disposal. It causes foul odor, breeding of flies and rodents, groundwater contamination, uncontrolled methane emissions, and frequent fire hazards. To overcome these problems, sanitary landfills were developed. Now let us understand the important components of a sanitary landfill. The first component is the bottom liner. The bottom liner is usually made of compacted clay and high-density polyethylene, commonly known as HDPE. Its main function is to prevent contaminated liquid from entering the soil and groundwater. For the UGC NET examination, remember this important point. The liner prevents groundwater contamination. Now let us discuss leachate. Leachate is a contaminated liquid formed when rainwater passes through solid waste and dissolves various pollutants. Leachate may contain heavy metals, organic compounds, pathogens, ammonia, nitrates, and toxic chemicals. If leachate reaches groundwater without treatment, it can seriously affect drinking water quality and aquatic ecosystems. Therefore, sanitary landfills include a leachate collection system. Perforated pipes placed at the bottom of the landfill collect leachate and transport it to a treatment plant before discharge. Another important component is landfill gas collection. Inside the landfill, biodegradable waste undergoes anaerobic decomposition. During this process, microorganisms produce gases, mainly methane and carbon dioxide. Methane is highly combustible and is also a powerful greenhouse gas. Modern sanitary landfills collect methane through gas wells and pipelines. Instead of allowing methane to escape into the atmosphere, it is used to generate electricity or heat. This helps reduce greenhouse gas emissions while producing renewable energy. Now let us discuss the daily cover. At the end of every working day, the deposited waste is covered with a thin layer of soil or other suitable material. The daily cover performs several important functions. It reduces unpleasant odors. It controls flies, insects, and rodents. It prevents waste from being scattered by wind. It also reduces the risk of fire. When the landfill reaches its maximum capacity, it is sealed using a final cover system. This cover consists of compacted clay, geomembranes, drainage layers, topsoil, and vegetation. The final cover prevents rainwater infiltration and minimizes environmental pollution after landfill closure. Now let us understand landfill management. Effective landfill management includes regular groundwater monitoring, leachate treatment, landfill gas monitoring, storm water drainage, slope stability, vegetation management, and post-closure monitoring. These activities ensure that the landfill remains environmentally safe throughout its operational life and even after closure. Now let us move to the second disposal method, incineration. Incineration is the controlled combustion of solid waste at very high temperatures. The main objectives are to reduce waste volume, destroy pathogens, and recover energy. Waste is burned in specially designed furnaces at temperatures generally ranging from 850 to 1100 degrees Celsius. During incineration, the volume of waste can be reduced by nearly 90%, while its weight can decrease by approximately 70%. The heat generated during combustion is often used to produce steam and electricity, making incineration an important waste-to-energy technology. Incineration is commonly used for municipal solid waste, biomedical waste, and certain hazardous wastes. However, incineration also has environmental challenges. If combustion is incomplete, harmful pollutants such as particulate matter, sulfur dioxide, nitrogen oxides, hydrogen chloride, dioxins, and furans may be released. Therefore, modern incinerators are equipped with advanced air pollution control devices such as electrostatic precipitators, bag filters, and scrubbers to remove pollutants before releasing gases into the atmosphere. Now let us compare sanitary landfills and incineration. Sanitary landfills require large areas of land but have relatively lower operating costs. Incineration requires much less land but involves high installation and operational costs. Landfills generate methane through anaerobic decomposition. Incineration reduces waste volume rapidly and can generate electricity. Both methods have advantages and limitations. Therefore, modern waste management follows an integrated solid waste management approach that combines recycling, composting, biomethanation, waste-to-energy technologies, sanitary landfills, and incineration instead of depending on only one method. Before moving to the next slide, let us quickly revise the important points. A sanitary landfill is an engineered waste disposal facility. Leachate is the contaminated liquid formed when water passes through waste. Methane is the major landfill gas. HDPE liners prevent groundwater contamination. Daily cover controls odor, pests, and litter. Incineration is the controlled combustion of waste at high temperatures. Dioxins and furans are harmful pollutants that may form during improper incineration. In the previous slide, we learned about the scientific disposal of municipal solid waste through sanitary landfills and incineration. However, not all waste is ordinary household waste. Many industries, hospitals, laboratories, mining operations, and manufacturing units generate waste that is much more dangerous. This type of waste is known as hazardous waste. Hazardous waste contains substances that can seriously harm human health and the environment if they are not managed properly. Even a small quantity of hazardous waste can contaminate soil, pollute groundwater, damage ecosystems, and cause long-term health problems. Therefore, hazardous waste requires special methods of collection, storage, transportation, treatment, and final disposal. Let us first understand the definition. Hazardous waste is any waste that possesses physical, chemical, or biological properties capable of causing significant harm to living organisms or the environment. For the UGC NET examination, you must remember the four major characteristics of hazardous waste. The first characteristic is ignitability. Ignitable wastes catch fire easily because they have a low flash point. Examples include petrol, benzene, alcohol, paint thinners, waste oils, and industrial solvents. Improper handling of ignitable waste may result in fires and explosions. The second characteristic is corrosivity. Corrosive wastes can corrode metals and damage living tissues. They usually have either a very low or a very high pH. Examples include sulfuric acid, hydrochloric acid, nitric acid, sodium hydroxide, and other strong acids and alkalis. Workers handling corrosive wastes must wear appropriate protective equipment because direct contact can cause severe burns. The third characteristic is reactivity. Reactive wastes are chemically unstable. They may react violently with water, air, or other chemicals. Some reactive wastes release toxic gases, while others may explode under certain conditions. Examples include sodium metal, cyanides, sulfides, and certain industrial chemicals. Such wastes require specialized storage and handling. The fourth characteristic is toxicity. Toxic wastes contain poisonous substances that may cause serious health problems even at very low concentrations. Examples include heavy metals such as lead, mercury, cadmium, chromium, and arsenic, as well as pesticides and industrial chemicals. These toxic substances may enter the human body through inhalation, ingestion, or skin contact. Many toxic chemicals accumulate in body tissues over time. This process is known as bioaccumulation. As these chemicals move through the food chain, their concentration increases at each trophic level. This phenomenon is called biomagnification. Mercury contamination in aquatic ecosystems is one of the best-known examples. Now let us study the major types of hazardous waste. The first type is industrial hazardous waste. Industries such as chemical factories, petroleum refineries, electroplating units, fertilizer plants, pharmaceutical industries, and textile industries generate hazardous wastes including chemical sludge, spent solvents, contaminated oils, and heavy metal residues. The second type is biomedical hazardous waste. Hospitals and healthcare facilities generate infectious wastes such as used syringes, contaminated dressings, pathological waste, laboratory cultures, and expired medicines. Improper disposal of biomedical waste can spread infectious diseases. The third type is agricultural hazardous waste. Agriculture generates hazardous waste in the form of pesticide containers, herbicide residues, insecticides, and chemical fertilizers. Improper disposal contaminates soil and nearby water bodies. The fourth type is electronic hazardous waste. Discarded computers, mobile phones, batteries, televisions, printers, and other electronic devices contain hazardous metals such as lead, mercury, cadmium, and chromium. Improper recycling exposes both workers and the environment to toxic substances. Now let us discuss the major sources of hazardous waste. Hazardous waste is generated from chemical industries, petroleum refineries, mining operations, thermal power plants, hospitals, research laboratories, agricultural activities, electronics manufacturing industries, and even households. Now let us understand the health impacts of hazardous waste. Hazardous chemicals may enter the human body through inhalation, ingestion, or skin absorption. Short-term exposure may cause skin irritation, eye irritation, headaches, nausea, breathing difficulties, and chemical burns. Long-term exposure is much more dangerous. It may lead to cancer, kidney damage, liver damage, neurological disorders, hormonal imbalance, reproductive disorders, birth defects, genetic mutations, and suppression of the immune system. Heavy metals deserve special attention. Lead mainly affects the nervous system. Mercury damages the brain and kidneys. Cadmium damages bones and kidneys. Arsenic is a well-known carcinogen. Chromium compounds may cause respiratory diseases and certain cancers. Therefore, hazardous waste management is not only an environmental issue but also a major public health concern. Now let us briefly discuss the basic principles of hazardous waste management. The first principle is waste minimization. Industries should reduce hazardous waste generation by adopting cleaner production technologies. The second principle is segregation. Hazardous waste should never be mixed with ordinary municipal solid waste. The third principle is safe storage. Hazardous waste should be stored in leak-proof and properly labeled containers. The fourth principle is safe transportation. Transportation should follow environmental regulations using approved containers and vehicles. The fifth principle is scientific treatment and final disposal. Depending on the characteristics of the waste, different treatment methods such as neutralization, oxidation reduction, precipitation, stabilization, solidification, incineration, and secure landfill disposal are used. These treatment methods will be discussed in detail in the next slide. Before moving to the next slide, let us quickly revise the important points. Hazardous waste possesses four major characteristics: ignitability, corrosivity, reactivity, and toxicity. Lead affects the nervous system. Mercury causes neurological disorders and biomagnification. Cadmium damages bones and kidneys. Hazardous waste should never be mixed with municipal solid waste. Waste minimization is the first priority in hazardous waste management. The next important question is, how is hazardous waste treated before its final disposal? Hazardous waste cannot be disposed of like ordinary municipal waste because it may contain toxic, corrosive, reactive, or flammable substances. Therefore, different treatment methods are used depending on the physical and chemical properties of the waste. Today, we will study the major hazardous waste treatment methods included in the UGC NET Environmental Sciences syllabus. Let us begin with neutralization. Neutralization is a chemical treatment process used mainly for acidic and alkaline wastes. In this method, acids are treated with alkalis, while alkaline wastes are treated with acids until the pH becomes nearly neutral. For example, sulfuric acid can be neutralized using lime or sodium hydroxide, whereas alkaline wastewater may be treated using hydrochloric acid. The main objective of neutralization is to reduce the corrosive nature of hazardous waste before further treatment or disposal. Now let us discuss oxidation reduction treatment, commonly called redox treatment. Some hazardous chemicals become less toxic when they undergo oxidation or reduction reactions. Oxidation is the process of adding oxygen or removing electrons, while reduction involves removing oxygen or gaining electrons. Oxidizing agents such as hydrogen peroxide, ozone, and chlorine are commonly used to destroy toxic organic compounds and cyanides. Reducing agents are used to convert highly toxic hexavalent chromium into the less toxic trivalent chromium. Redox treatment is widely used in chemical industries and wastewater treatment plants. The next treatment method is precipitation. Precipitation is mainly used to remove dissolved heavy metals from wastewater. In this process, chemicals such as lime, sodium hydroxide, or sodium sulfide are added to wastewater. These chemicals react with dissolved metals and convert them into insoluble solid particles called precipitates. The precipitated solids are then separated through sedimentation and filtration. This method is commonly used for removing lead, cadmium, chromium, copper, zinc, and nickel from industrial wastewater. Now let us study solidification. Solidification is a physical treatment method that reduces the mobility of hazardous waste by converting it into a solid mass. Hazardous waste is mixed with materials such as cement, fly ash, lime, or asphalt. These materials surround the waste particles and reduce the possibility of leakage into the environment. Solidification mainly improves the physical strength of the waste and makes transportation and disposal safer. Closely related to solidification is stabilization. Students often confuse these two methods. Remember this important difference. Solidification mainly changes the physical form of the waste. Stabilization mainly changes the chemical properties of the waste, reducing its toxicity and mobility. During stabilization, chemical reactions convert hazardous substances into more stable and less soluble compounds. As a result, harmful chemicals are less likely to leach into soil and groundwater. Very often, stabilization and solidification are used together before final disposal in secure landfills. Now let us discuss incineration. Incineration is the controlled burning of hazardous waste at very high temperatures, generally above 1000 degrees Celsius. It is particularly suitable for hazardous organic wastes, biomedical waste, pharmaceutical waste, pesticides, solvents, and contaminated chemicals. The major advantages of incineration are significant reduction in waste volume, complete destruction of pathogens, and recovery of thermal energy. However, improper incineration may release harmful pollutants such as dioxins, furans, nitrogen oxides, sulfur dioxide, and particulate matter. Therefore, hazardous waste incinerators are equipped with advanced air pollution control devices such as scrubbers, bag filters, and electrostatic precipitators. Finally, let us discuss secure landfill disposal. After hazardous waste has been treated, some residues still require final disposal. These residues are placed in specially designed secure landfills. Secure landfills are different from ordinary sanitary landfills. They have multiple protective liners, leachate collection systems, groundwater monitoring wells, landfill gas management systems, and long-term environmental monitoring. Their primary objective is to isolate hazardous waste from the surrounding environment and prevent contamination of soil and groundwater. Now let us summarize the treatment methods. Neutralization is used for acidic and alkaline wastes. Oxidation reduction changes hazardous chemicals into less toxic forms. Precipitation removes dissolved heavy metals from wastewater. Solidification converts hazardous waste into a solid mass. Stabilization reduces the chemical mobility and toxicity of hazardous substances. Incineration destroys hazardous organic wastes at very high temperatures. Secure landfills provide the final environmentally safe disposal of treated hazardous waste. For the UGC NET examination, remember these important points. Neutralization is used for acids and alkalis. Precipitation removes dissolved heavy metals. Solidification changes the physical form of waste. Stabilization changes the chemical properties of waste. Incineration is suitable for combustible hazardous waste. Secure landfills are used for the final disposal of treated hazardous waste. These concepts are frequently asked in statement-based and matching questions. E-waste and fly ash. Both e-waste and fly ash are major environmental concerns. However, if they are managed scientifically, they can also become valuable resources. Let us first understand e-waste. E-waste, or electronic waste, refers to discarded electrical and electronic equipment that has reached the end of its useful life. Examples include computers, laptops, mobile phones, televisions, refrigerators, washing machines, printers, air conditioners, batteries, circuit boards, cables, and other electronic devices. With rapid technological development and frequent replacement of electronic products, e-waste has become one of the fastest growing waste streams in the world. Now let us discuss the classification of e-waste. For the UGC NET examination, e-waste can be broadly classified into 4 categories. The first category is large household appliances, such as refrigerators, washing machines, air conditioners, and microwave ovens. The second category is small household appliances, including vacuum cleaners, electric irons, mixers, toasters, and electric kettles. The third category is information and communication technology equipment, which includes computers, laptops, printers, mobile phones, telephones, routers, and servers. The fourth category is consumer electronics, such as televisions, cameras, music systems, and audio-video equipment. Now let us understand why e-waste is considered hazardous. Electronic devices contain valuable materials such as gold, silver, copper, aluminium, and rare earth elements. However, they also contain hazardous substances including lead, mercury, cadmium, chromium, brominated flame retardants, and certain toxic plastics. If e-waste is disposed of improperly, these toxic substances may contaminate soil, groundwater, and surface water. Burning electronic waste releases toxic gases into the atmosphere, while informal recycling exposes workers to dangerous chemicals. Therefore, e-waste requires scientific management. Now let us study the management of e-waste. The first step is collection. Used electronic products should be collected through authorized collection centers. The second step is segregation and dismantling. Different components such as plastics, glass, metals, batteries, and circuit boards are separated. The third step is recycling. Valuable metals including gold, silver, copper, and aluminium are recovered using specialized recycling technologies. The fourth step is the safe disposal of non-recyclable hazardous components using approved treatment facilities. One important concept from the UGC NET examination is Extended Producer Responsibility, or EPR. Under EPR, manufacturers are responsible for collecting and environmentally managing electronic products after consumers discard them. This encourages producers to design products that are easier to recycle and generate less hazardous waste. Now let us move to fly ash. Fly ash is a fine powder produced during the combustion of pulverized coal in thermal power plants. When coal burns, the lighter ash particles are carried upward with flue gases. These particles are captured using electrostatic precipitators or bag filters before the gases are released into the atmosphere. The collected fine particles are called fly ash. Now let us discuss the composition of fly ash. Fly ash mainly contains silica, alumina, iron oxide, calcium oxide, magnesium oxide, and small quantities of trace elements. The exact composition depends upon the type of coal used. If fly ash is not managed properly, it can create serious environmental problems. Wind may carry fly ash over long distances, causing air pollution. Rainwater may transport ash into nearby rivers and lakes, leading to water pollution. Improper disposal may also contaminate soil and groundwater. However, today fly ash is considered a valuable industrial resource rather than simply waste. Now let us study the utilization of fly ash. Fly ash is widely used in the manufacture of cement and concrete. It is used to produce fly ash bricks, which are lighter, stronger, and more environmentally friendly than conventional clay bricks. Fly ash is also used in road construction, embankments, mine filling, land reclamation, and as a soil amendment in certain agricultural applications. Utilization of fly ash reduces the requirement for natural clay, conserves topsoil, decreases landfill demand, and lowers greenhouse gas emissions associated with brick manufacturing. Now let us quickly compare e-waste and fly ash. E-waste is generated from discarded electrical and electronic equipment and contains both valuable metals and hazardous substances. Fly ash is generated from coal-fired thermal power plants and mainly contains mineral oxides. Both require scientific management. Both can cause environmental pollution if disposed of improperly. Both also provide opportunities for resource recovery and recycling. For the UGC NET examination, remember these important points. E-waste is one of the fastest growing waste streams in the world. Lead, mercury, cadmium, and chromium are major hazardous components of e-waste. Extended Producer Responsibility, or EPR, is an important concept in e-waste management. Fly ash is generated from thermal power plants during coal combustion. Fly ash is widely used in cement, concrete, fly ash bricks, road construction, mine filling, and land reclamation. These points are frequently asked in multiple choice and statement-based questions. Plastic waste management. Plastic has become an essential part of modern life. It is lightweight, durable, waterproof, inexpensive, and easy to manufacture. Because of these properties, plastics are widely used in packaging, agriculture, healthcare, construction, transportation, electronics, and almost every aspect of our daily lives. However, the same properties that make plastic useful also make it one of the most serious environmental pollutants. Most conventional plastics are non-biodegradable, which means they do not decompose naturally for hundreds of years. As a result, plastic waste accumulates in landfills, rivers, lakes, oceans, forests, and agricultural lands. Now let us understand the major sources of plastic waste. Plastic waste is generated mainly from packaging materials such as plastic bags, bottles, food wrappers, disposable cups, and containers. Other important sources include households, industries, hospitals, agriculture, construction activities, fishing industries, electronic products, and commercial establishments. Among all these sources, single-use plastics contribute significantly to plastic pollution because they are used only once and then discarded. Examples include plastic carry bags, disposable plates, straws, cutlery, stirrers, and packaging films. Now let us discuss the environmental consequences of plastic waste. The first impact is soil pollution. Plastic waste blocks soil pores, reduces water infiltration, affects soil aeration, and decreases soil fertility. The second impact is water pollution. Plastic waste enters rivers, lakes, and oceans through runoff and improper disposal. Marine organisms often mistake plastic for food, leading to injury, starvation, and death. The third impact is air pollution. Open burning of plastic releases toxic gases such as dioxins, furans, hydrogen chloride, and carbon monoxide, causing serious health and environmental problems. Plastic waste also blocks drainage systems, resulting in urban flooding during heavy rainfall. Another major concern is its impact on wildlife. Birds, fish, turtles, and other animals often become entangled in plastic waste or ingest plastic particles, which may eventually cause death. Now let us study one of the most important topics for the UGC NET examination: microplastics. Microplastics are plastic particles smaller than 5 millimeters. They are produced either by the breakdown of larger plastic materials or are manufactured intentionally for industrial and cosmetic purposes. Examples include fibers released from synthetic clothes, tire wear particles, cosmetic microbeads, and fragments of plastic bottles and bags. Today, microplastics have been detected in oceans, rivers, drinking water, agricultural soils, air, seafood, and even in the human body. Scientists are concerned because microplastics may carry toxic chemicals and enter the food chain, posing potential risks to both ecosystems and human health. Now let us discuss plastic waste management. The most effective strategy is to follow the 5 Rs. The first R is refuse, which means avoiding unnecessary plastic products, especially single-use plastics. The second R is reduce, which means minimizing plastic consumption. The third R is reuse, which encourages using products multiple times instead of discarding them after one use. The fourth R is recycle, where plastic waste is collected, sorted, cleaned, shredded, melted, and converted into new plastic products. The fifth R is recover, where non-recyclable plastics are converted into energy through technologies such as pyrolysis or used as refuse-derived fuel in cement industries. Only the remaining non-recyclable waste should be sent for scientific disposal. Now let us discuss an important regulation. In India, plastic waste management is governed by the Plastic Waste Management Rules, 2016, along with subsequent amendments. One of the most important concepts introduced under these rules is extended producer responsibility, commonly known as EPR. Under EPR, manufacturers, importers, and brand owners are responsible for collecting, recycling, and environmentally managing the plastic waste generated from their products. This policy encourages industries to design environmentally friendly packaging and improve recycling systems. The Government of India has also imposed restrictions on several categories of single-use plastics to reduce plastic pollution and promote sustainable alternatives. Before we conclude this unit, let us understand one final concept: Integrated Solid Waste Management, or ISWM. Integrated Solid Waste Management combines waste reduction, segregation, collection, recycling, composting, biomethanation, energy recovery, and scientific disposal into one comprehensive system. Instead of depending on only one technology, ISWM uses multiple approaches to maximize resource recovery and minimize environmental pollution. For the UGC NET examination, remember these important points. Plastic is non-biodegradable. Microplastics are plastic particles smaller than 5 millimeters. Single-use plastics are a major source of plastic pollution. Extended producer responsibility makes producers responsible for managing plastic waste. Plastic Waste Management Rules, 2016, are important from the examination point of view. Integrated Solid Waste Management combines multiple treatment and disposal methods for sustainable waste management. With this, we have successfully completed Unit 7, Solid and Hazardous Waste Management. Thank you for learning with Rush Learning Hub. Keep learning, keep growing, and all the very best for your UGC NET examination. See you in the next lecture. If you found this video helpful, please like, share, and subscribe to Rush Learning Hub for more complete UGC NET lectures.